Our current models of physics rely on the existence of discrete things, particles that act like tiny billiard balls, waves that travel through vacuums, and molecules with fixed structures. To test the relational action framework, we have to assume these objects are secondary. We need to look past the sphere and focus on the web of connective tension that holds it together. The core axiom of RAF is that reality is built from relationships that stabilize into patterns. When these relationships reach a point of relational closure, they fold into a pattern stable enough to appear to us as solid physical matter. In this model, light is a boundary resolution event. A photon is not a projectile moving through a void. It is the measurable result of two patterns interacting at their perimeters. RAF provides a specific, falsifiable hypothesis that identifies where reality should deviate from standard predictions. If the framework is correct, we have been measuring the properties of objects when we should have been measuring the stability of the connections between them. This falsification map serves as a guide for researchers, pointing to specific experimental tripwires in the quantum base, the biological scale, and the universal constants. We can contrast the standard model's geometric predictions with the topological results predicted by RAF. At the quantum level, the map targets the behavior of optical cavities and the precision of single photon sensors. At the biological scale, the focus shifts to cellular signaling oscillations and the large-scale patterns of the brain and heart. Finally, the map identifies the fine structure constant, the ratio 1/137, as a primary site for testing the absolute stability of relational patterns under extreme stress. By defining these failure points, RAF moves from theory into an experimental roadmap. If a photon is a resolution at a boundary, then the structure of the detector itself should influence the detection event in ways current models do not account for. Testing this requires observing superconducting photon sensors. Different detector geometries should produce subtle variations in detection behavior that cannot be explained by standard electromagnetic absorption alone. Fundamental particles like electrons or muons are viewed here as topological knots, patterns that have reached a stable state of closure. This means particle decay is the transformation of one pattern into another, rather than the literal destruction of an object. Quantum entanglement offers a direct test of whether relationship or distance is more primary. RAF predicts that entanglement is a relational connection existing independently of geometric space. In this view, close describes the strength of the relationship, not physical distance. In extreme systems, we should find that geometric measurements fail before correlation between the 2 points drops. Identifying relationship as the primary variable removes the non-local paradoxes from quantum mechanics. Biology provides a high-stakes environment for these tests because the relational patterns involved are incredibly complex. Standard medicine looks for chemical failures, a broken molecule, or a localized cell death, which then lead to observable symptoms. However, if the system is held together by relational closure, then a breakdown in the fit of the overall network should occur before the individual molecules fail. This is known as network frustration. First, we can hunt for this preliminary frustration by analyzing EEG data. We are looking for the exact moment the system's oscillations begin to lose their global coherence. Roth predicts that this drop in coherence serves as an early indicator of system stress. The network stops fitting together correctly, creating a measurable irregularity that precedes localized physical damage. Next, cardiac dynamics and heart rate variability provide a second testing ground. We can monitor the rhythm for signs that the biological fit is beginning to oscillate irregularly. These irregular patterns represent the system failing to maintain its relational structure under the stress of disease. If disease begins as a loss of coherence, medicine could potentially detect and treat the breakdown of the network before the molecules physically break. We can extend this framework to the laws of the universe, starting with the work of James Clerk Maxwell. RAF suggests that electromagnetism is the set of rules that maintains consistent phase relationships across space. Researchers can test this by using metamaterials to manipulate phase structures. If field behavior changes more than classical theory allows, it suggests the phase relationship is the more primary variable. Space and time may also be emergent rather than fundamental, meaning they could decouple or fail independently under extreme conditions. In highly coherent systems, we expect to find regimes where temporal order remains stable, even as the spatial geometry breaks down. This brings us to the fine structure constant, often treated as an arbitrary value found in nature. In this framework, the constant is a stability ratio. It represents the point where the smallest possible relational closure interacts with the surrounding field. Our universal constants may simply be the boundary rules that emerge from a hyper-relational network. We see this efficiency in photosynthesis. Energy in a leaf doesn't bounce randomly. It follows structured pathways that guide it directly towards resolution. The leaf's structure is optimized to resolve light at the boundary with minimal energy loss, using the pattern to direct the flow. If biological systems use these optimized pathways to handle energy, the human brain may function similarly by using relational structure to maintain stable signal patterns. When the brain achieves a state of maximum coherence with no gaps or frustration in the network, we experience a flow state. It is the psychological experience of a system reaching perfect relational closure under stress. In this model, intelligence is measured by how effectively a system can maintain that coherence when the environment tries to disrupt the pattern. The meta-prediction of RAF is that the pattern is the primary driver of reality, and everything we observe is a downstream consequence. Matter is a stable pattern, biology is an adaptive one, and disease is its breakdown. If reality is built from relational closure, physical and biological systems will show a dependence on pattern coherence and topology that current models cannot explain. The relational action framework provides a set of coordinates where our current understanding of physics is likely to break. All that remains is for us to look where the map points.